speaker, Laura. Maybe you can start sharing your screen.
Hello, yes, first I'll turn on my video and unmute, and then go ahead and share my screen, which for the moment should be empty.
It shows a mountain. I'll use a view of the mountain. Okay, wonderful. So our next speaker is Laura Jeanty from the University of Oregon, and she will tell us about future perspectives at the high luminosity LHC. Please go ahead, Laura.
Okay, thank you very much to the organizers for the invitation. Like Veronica, I was in Pittsburgh about 8 years ago for my last PHENO, so maybe I'll be there again before the next 10 years. Today I'm here to talk about prospects for the high lumi LHC. So moving from Tulika's talk of the morning and then inspired by Veronica's talk from the LHC to the high lumi LHC, just to summarize in 2 sentences, the LHC over the last 10 years has illuminated a whole landscape of the standard model and beyond. We've heard about how well the standard model has performed, with a couple of very interesting and important exceptions, mainly coming from flavor anomalies. The standard model now includes the Higgs, and these measurements are impressive and growing. And there's been a broad suite of searches for new physics, both direct and indirect, which have so far unveiled where the new phenomena are not. But the high lumi LHC over the next 15 to 20 years will provide more than an order of magnitude more luminosity. The goals of the high luminosity LHC include a deeper understanding of the Higgs boson, precision measurements from QCD to electroweak physics, the Higgs boson, flavor physics, and probing beyond the standard model in both direct and indirect precision measurements and searches. The potential for the discovery at the high luminosity LHC is broad. In this talk, I'm going to only take a few selective projections, either from ATLAS, LHCB, or CMS. In the case that I choose ATLAS or CMS, the sensitivity we expect is similar, and so it's just a matter of personal preference which I choose. And I'm going to talk about the detector upgrades and try to connect them to our sensitivity, as well as our challenges and opportunities that we will face moving forward. So the high luminosity LHC, which will start around 2025, will give us, as Tulika said, 95% of the data of the entire LHC program. We expect a total of at least 3,000 indoor femtobarns at a center of mass energy of 14 TeV. And to get this large luminosity, we will have to have a much higher instantaneous luminosity, giving us a pileup of between 140 and 200 collisions per crossing. And this, of course, comes with its own challenges. So the high instantaneous as well as integrated luminosity that we expect for the high luminosity LHC brings challenges in all areas, from the detector itself having to deal with a higher occupancy, higher data rate, and higher total radiation dose, to the trigger, reconstruction, performance, and analysis challenges. So every aspect of our work as experimentalists will be challenged by this higher luminosity, but with it comes the opportunities of much more data and much more possibility for measurement and discovery. The detectors are undergoing extensive upgrades to be able to handle the challenges of both the instantaneous and integrated luminosity. In many cases, the goal is simply to maintain the performance that we've already become accustomed to, which is challenging with more luminosity. But in some cases, we're actually adding new functionality or improving our performance, which will allow us to probe even deeper into some of the corners of phase space still remaining. I'm going to start looking at just highlighting some of the major upgrades from the 3 experiments. Just touching on a few, there's vast work going on, so I won't have time to cover them all. But I'll start with the common features for both ATLAS and CMS. So first, for both ATLAS and CMS, the inner detector, of course, is the part of the system that's most sensitive to radiation and sees the highest occupancy. So both experiments will remove our current inner trackers and replace them with entirely new inner trackers, which will be all silicon and a combination of pixels and strips. To handle the increased pileup and maintain the nice trigger thresholds that we've become accustomed to, there will be massive updates to the trigger and data acquisition system with nearly an order of magnitude higher trigger rate at both level 1 and the high level trigger. To handle the higher occupancy as well as the higher data rate and trigger required by the trigger performance, there are also very extensive upgrades to both the muon and calorimeter systems, to the electronics, and for the Atlas muon system, we're actually getting an entire new NCAP muon system right now. And to help with pileup projection in the higher collision environment, Atlas is getting a new NCAP timing detector with about 30 picosecond resolution for minimum ionizing particles, which will help resolve the time dimension of the beam spawn. CMS's upgrade program in broad scopes is very similar. Some of the differences, so CMS is getting both a barrel and an NCAP timing detector. I'm not going to talk about it here, but the barrel timing detector of CMS does propose some interesting possibilities for long-lived particle searches. So if you're interested, I encourage you to check those out. The inner tracker from CMS also includes in the outer strips layer, the ability to trigger on very short track stubs at level 1, which is a nice new capability that CMS is adding. Similarly to Atlas, major upgrades to the trigger data acquisition system, the NCAP calorimeters, as well as the muon system. And CMS is also installing a new NCAP calorimeter, which will have the ability to reconstruct showers in 3 dimensions. Moving to LHCB. So LHCB has a different luminosity profile than both Atlas and CMS, where we expect at least 3,000 inverse femtobarns by the end of run 5. LHCB will have, by the end of run 5, will have 300 inverse femtobarns. So I've put the luminosity profile here. LHCB is actually undergoing their major upgrade right now in preparation for run 3. And one of the main motivating factors of their upgrade is to actually upgrade the trigger system to be a triggerless readout, meaning that at level 1, they read out all collisions at 40 megahertz. And then some event selection can be done in pure software at the high level trigger. Now, this is a major upgrade, which requires significant changes to the detector, including, for example, a new tracker, which is needed not only for the triggerless readout, but also for the higher occupancy and data rate that we expect in the increased luminosity of run 3 and 4. As well as upgrades to the calorimeters and muon systems to handle the higher luminosity and to be able to do the triggerless readout. So if we've learned anything in the last year, it's that forecasting is a very fraught exercise. It's incredibly difficult to do well. But it's important, and there's been a vast community effort over the last years, stretching from the European Strategy for Particle Physics, which was completed last year, to the US SNOMAS process, which is underway, to motivate and understand our potential for the high luminosity LHC. So there are a number of reports, which I've linked here, if you're interested in the full suite of projections. But in general, predicting the future is hard. Here I've listed more or less in increasing order of difficulty some of the things we have to take into account when we're trying to project our sensitivity. So the increase in energy, that's the easiest thing to account for. Handling increased data and the effect that has on statistical uncertainty is also fairly straightforward. Many analyses that I'm showing in projections here sort of stop there, and they're really projections from our run 2 performance. That gives you, an understanding of if everything else were to stay the same, where would we be? Some cases we expect significant improvements from the impact of new detector capabilities or improvements in performance. So in some cases that's considered. Now, forecasting the influence of or the impact of what our systematic uncertainties will do is quite difficult. So as part of the European Strategy for Particle Physics, there was an agreement made between Atlas and CMS about how to project systematic uncertainties. So if it's data statistics, those are easy. You can improve by square root of luminosity. we set the Monte Carlo statistics to 0, and then either assume the same performance we have now or study with dedicated simulation the expected performance from the detector. And then we expect our theory colleagues to be working as hard as we are. So we forecast that the theory uncertainties can be cut in half. And then in the cases where it's relevant, we do some detailed studies on the PDF uncertainties. So for some cases, these reduced systematics, we explore the effect of these, and they can have quite profound impacts on the results that we achieve. Now, of course, in some sense, these assumptions can be thought of as optimistic. We assume certain uncertainties will go to 0 or can be reduced, which is certainly not for free. But in many cases, we also extrapolate these results based on our current analyses and techniques, which we, in some sense, is also pessimistic. We expect that these will improve a lot. We've certainly seen that over the last 10 years. And this is where a lot of the interesting work on the analysis side will go into the future. Okay, so starting with the easy part. So this is what we expect in increase from 13 to 14 TeV in terms of the cross section for certain processes. So if you're interested in, for example, di-Higgs production, you get about a 20% increase from the increased energy. And if we look at, for example, strongly produced, let's say, gluinos in supersymmetry, or your favorite resonance, you can expect up to a factor of 2 increase. So of course, the heavier process you're looking for, the more the center of mass energy will help. All right, so I'm going to start with some of expectations, selective expectations for how our measurements of the standard model will improve. So starting with the Higgs, which of course is a major benchmark of the and major goal of the highly massy LHC, to measure the couplings and measure them quite precisely. So we expect, so here in these two plots, I'm showing by production mode and by decay mode, what we expect our sensitivity or a measurement of the couplings to be. And you can see that for all but the rarest couplings, we expect to be able to constrain them to the 2 to 7% level. So this is really precision measurements of the Higgs boson. And even rare channels like dimuon or Z gamma, we expect to be able to constrain. All these will be limited by statistics. For the main channels of measuring the Higgs couplings, the systematics dominate. And just to give you a sense, in many cases, these are driven by effects of pileup. For example, from gamma-gamma, the largest uncertainties we expect are from the pileup effects on reconstructing and identifying photons. And similarly for WW, the largest uncertainty comes from the knowledge of the WW background, which is related to fake leptons, and as well that is related to our understanding of the effect of pileup on lepton reconstruction. Now, twice the Higgs is twice as good. So again, a keystone goal of the high luminosity LHC is to be able to observe di-Higgs production. That gives us direct access to the shape of the Higgs potential and allows us to access the Higgs self-coupling, this kappa gamma, which can be sensitive, very sensitive to physics beyond the standard model. This potentially has implications for electroweak baryogenesis. Right now, our limit is about 4 times the standard model. And so we expect to significantly improve this with the high luminosity LHC. By the end of Ren 5, we expect to have about at least 3 sigma observation significance within each experiment from a combination of channels. And you can see the channels that we expect to input here. Now, the channels that are most sensitive aren't necessarily the ones with the largest contribution or the largest branching ratios. That's partly because we expect there to be large systematic uncertainties on, for example, the 4B background. And so we expect BB tau tau and BB gamma gamma to dominate the measurements. There's already been improvements in these measurements in Run 2 since these projections were made, just as an example of how fast things can move. But we do expect the largest uncertainties here to be ultimately statistical, and on the effect not only of selecting the signal, but also on our ability to, for example, understand the background performance and BJet tagging. Moving into electroweak physics, so trying here again to observe processes that give us a window into electroweak symmetry breaking. One of the goals, longstanding goals of the LHC is to be able to have sensitivity to the longitudinal polarization of diboson scattering. So here I'm showing the sensitivity as a function of luminosity for both WZ and WW left-handed polarization scattering. So these channels have been studied separately. We expect to get from each channel up to 3 sigma sensitivity for this left-handed process from actually studying the shape of the dijet separation in the azimuthal direction. That gives us sensitivity to distinguish between other production modes of WZ and WW. So here the uncertainties are dominated by a number of things. So for example, by our ability to reject fake leptons and by jet energy scale and resolution. In both cases, actually the increased tracker acceptance and rapidity really helps these analyses by allowing us both to better reconstruct the forward jets, which are used in this dijet azimuthal distribution, as well to improve signal acceptance, both for the leptons from the diboson decays, as well as to be able to reconstruct the lower PT jets. And here again is a case where we expect potentially analysis improvements to improve the sensitivity. Moving the standard model into very precise measurements. So looking at the W mass. So the W mass is an essential ingredient to our standard model fits. Right now, the fits, excluding the W mass, have a sensitivity of about 8 MeV on the W mass, whereas the combined measurement of the W mass is significantly larger than that, in about 15 MeV. And so this is a goal to be able to reduce the W mass uncertainty as it's measured to below 8 MeV. So Atlas has looked at this in the context of the high luminosity LHC. We expect to take low pileup data to be able to measure the hadronic recoil of the W mass and gain sensitivity to the precision WPT, which is an input to the W mass. If we were able to collect more than 260 inverse picobarns of low mu data, we expect the dominant uncertainty on the W mass to actually come from PDFs or knowledge of PDFs. And so being able to reduce our PDF uncertainty is a major goal. Doing that requires a number of measurements where the extended rapidity actually is an important addition, which allows us to further constrain the PDFs. And you can see here, I've highlighted in purple how the actual increased ADA acceptance of the tracker significantly decreases the expected uncertainty on the W mass from 16 to 12 MeV. So one of the inputs to the PDFs, of course, comes from top physics, but we expect that in the high luminosity LHC, we'll be bringing top physics from the current precision range into the ultra precision range, allowing precision measurements, for example, of the top mass, as well as of double differential distributions, which is shown here, for example, the invariant mass and rapidity of TT bar pairs, which can be a useful input to PDF fits. We're also interested in rare top processes. So we expect to be able to constrain the 4-top cross-section to almost 10%, including multiple channels, which are shown here with different jet and B-jet multiplicities, and to be able to measure very rare top processes like TT gamma to 3% and be able to do differential distributions there. Looking at even rarer processes, we turn to the measurements of very, very rare decays, which LHCB has pioneered. So when we move to these very rare processes, we open a window to precision tests of the standard model, as well as a window to the possibility of contributions at even higher mass scales that are contributing. This is the current measurement from LHCB of 2 very rare decay modes of Bs. And so this is the current sensitivity, and just to give you a sense of how we expect this to improve, One way of quantifying this is by looking at the ratio of these two processes. So that's currently about 90%. We expect by the end of run 3 with this 23 or 25 inverse femtobarns to get this down to 30%. And by the end of run 5 to get this down to about 10%. So here, the beta mu mu will be limited by statistics, where the BS will be limited by systematics. And assuming the same detector performance as now, we expect to be able to reduce those systematic uncertainties to about 4%. Now, these measurements are precise enough that actually they'll have limiting sensitivity over many corners of the supersymmetric MSSM phase space just from these precision measurements alone. And moving into the sector, which is very interesting right now, given the current tension we see in some lepton flavor universality tests with the standard model. So on the top here is the measurement, the current measurement from LHCB of RK. So the ratios here Tulika defined, the branching ratios of the bees to various final states. So this shows some tension with the standard model. And if we look forward to our ability to reduce the uncertainty on this measurement with future data, we expect the ultimate precision of, for example, of RK and RK star to be better than 1% with the 300 inverse femtobarn. That will allow us to distinguish above 5 sigma many scenarios of new physics. So on the bottom, these 4 scenarios are different scenarios of new physics with different Wilson coefficients that correspond to the current excesses. And you can see that we would be able to resolve them all beyond 5 sigma from the standard model prediction of 1. We also expect to be able to have sensitivity to other rare decay modes, including, for example, our pi. So this is quite an exciting area for future measurements. Okay, so now let's move from beyond the standard model measurements and the indirect probes that they give us to beyond the standard model physics to the direct searches. I'm going to start here with searches for very light, very weakly coupled particles. These are an important element of our search program, and dark photons are a classic benchmark. Though there's a whole class of interesting searches. We heard from Veronica from axions to ELPS, which are all very well motivated, and which all require the ability to reconstruct very low PT objects and have access to weakly coupled low mass things. So this is a projection from LHCB of their sensitivity after different either 50 or 300 inverse femtobarns to dark photons as a function of the mass of the dark photon and the coupling. And this takes in a number of techniques from searches using the dimuon spectrum to long-lived searches at the lower epsilon couplings to looking for the very low mass E+ E- pairs, which are produced from a dark photon in the decay of D mesons. So with this full suite of techniques, which all rely on actually the triggerless readout in order to get the statistics at the low muon or more or low electron PTs, LHCB expects to be able to have sensitivity to almost the entire low mass, low coupling plane that's currently not covered. Okay, keeping on the theme of searches for light neutrals, we move to searches for Higgs to invisible. So the Higgs is an excellent, still new tool and gives us a window into other sectors, including potentially, we hope, the dark sector. And so Higgs to invisible is an excellent probe for very model independent, for example, light dark matter. So right now, the current limit on Higgs to invisible is about a branching ratio of about 11%. This is driven by vector boson fusion. And as we move into the high luminosity era, we expect all the background composition will change a bit due to the increased rapidity and the ability that gives us to reject background, that the VBF production will continue to dominate. So here, being able to tag those two forward jets and reject pileup jets is also paramount. And so both the increased ADA acceptance of the tracker, as well as the timing detectors, which allow us to timestamp the jets and really reject pileup jets are important for both experiments. We expect individual channels from CMS and ATLAS to be able to reach 4% on the branching ratio of Higgs to invisible, and the combination to give us a precision of up to 2.5%. And the systematics here vary depending on the channel that you're looking at, but in many cases, it's actually the systematic uncertainties we expect to dominate. And that's assuming, for example, that we can get the luminosity uncertainty down, from the current value of about 2.5%. This is actually an old value, but keep it at 1% for the high luminance LHC. So this is a whole other challenge that we have not yet even mentioned. Okay, looking beyond Higgs to invisible for more generic searches for dark matter. In this case, dark matter produced in conjunction with some other objects. So these are sort of generically called mono X searches, mono top, mono Z, mono jet. So pushing our sensitivity to both heavier dark matter masses as well as down in the coupling between the dark matter mediator and the standard model is an important part of the dark matter program at the LHC. We expect in some cases that the mono X, for example, the mono jet sensitivity will be competitive with direct searches for example, neutralinos from supersymmetric searches, giving us sensitivity up to, for example, 200 or 300 GeV for Higgsino or WeNo neutralinos, a nice candidate for dark matter. Here, we're very sensitive to systematic uncertainties. So you can see in the left-hand plot, this is our expected exclusion sensitivity for mono Z. You can see that if you only take the statistical uncertainties, it's the sensitivity is the dashed line up to about 1600 GeV for massless dark matter candidates. If you take the current projections of our systematics, you're down to 1400 GeV. And this hybrid approach I talked about at the beginning of some assumptions about how our systematic uncertainties might scale will give you 1500 GeV sensitivity. So we're quite sensitive to the impact of our systematic uncertainties, and that will be an area we have to work on moving forward. Okay, moving to the very highest masses we can directly probe. So looking for resonances here, just to give a sense of the impact of moving from 13 to 14 GeV, where this is most visible in the search for very heavy objects. So we've looked at resonance decaying to a broad variety of things, from TT bar to lepton pairs. We expect to have sensitivity to, for example, Z primes up to discovery sensitivity above 6 TeV. And for W primes discovery sensitivity approaching 8 TeV. And so here we're really taking advantage of the increased energy and data set to really probe the highest direct sensitivity we have to very heavy new physics. In supersymmetry, the challenge is not at the very highest mass scales, but for example, looking for electroweak which have lower mass and lower cross-section, and especially compressed scenarios where the mass differences between different supersymmetric partners is small, and therefore the visible decay products that we're looking for are very low PT. Here, maintaining or even improving our detector's ability to reconstruct very soft objects from taus to B-jets, as well as our missing ET resolution is very important, especially in the face of larger pileup. Just as a broad summary, if you look along the x-axis here at our sensitivity for electroweak or our STAUs, we expect about an improvement of 500 GeV for the massless neutralino case compared to our current sensitivity. And improvements in our techniques, for example, the ability to tag soft objects, creative ideas like exploring photon production, or more advanced machine learning techniques will allow us to push farther into the compressed region. And so all of these techniques combined, we expect to be able to cover most of the natural electroweak SUSY parameter space by the end of the high luminosity LHC, although this really will rely on continued improvements in our analysis techniques.
2 minutes, Laura.
Perfect. So I'd like to end with a short case study on how things change with a new detector, because it's not always intuitive. So I'm looking at let's say, one challenge and one opportunity, or vice versa, from the Atlas Inner Tracker, the new Atlas Inner Tracker, in the arena of long-lived particle searches. So this is a hybrid picture. On the left is the current inner detector, and on the right is the new inner detector. You can see we'll get rid of the transition radiation tracker in Atlas, and we'll take our pixel and strip detector and sort of expand them. So we'll have one more pixel layer, but the whole thing will be expanded to fill the current volume. And so the impact this will have on different searches for long-lived particles varies. So the first is displaced vertex signature. So this search looks for either a charge or neutral object that travels some distance and decays inside of the inner detector. This is sensitive to a huge variety of new particles, and you can look for that displaced vertex in conjunction with essentially anything you want. Here, in order to reconstruct, you have to look for the tracks that come after the decay, and you need a minimum number of silicon hits in order to well reconstruct that track. So the sensitivity is very sensitive to the detector geometry. Expanding the inner detector gives you more volume to look for your displaced track. So if you compare on the left-hand side, the gray to the blue, the gray is the current detector and the blue is the future detector, you can see that as a function of where this long-lived particle decays, we actually expect significant improvement in our acceptance of the displaced tracks from the new detector just due to this change in geometry. And that will translate into an increase in sensitivity at longer lifetimes just from the detector geometry. And so this is an area we actually expect to win from the new tracker. In contrast, disappearing tracks is a classic benchmark for a wide class of natural dark matter models, including scenarios where you have pure WENOs or Higgsinos. And here you're looking for a very short chart from a charged particle that decays to essentially invisible. And so you have to reconstruct that short track before it decays. And so you're looking for a minimum number of silicon hits before it decays. So here, actually expanding the tracker hurts our sensitivity because the particle has to decay farther away in order to get that minimum number of silicon tracks. And so in the dotted lines here is the run 2 acceptance as a function of the radius, and the solid is what we expect for the high luminous LHC detector. And so you can see it's a small difference, but that translates into a major impact in the acceptance we expect for the lifetime of, for example, a pure WENO and Higgsino. And so as we look to the high luminous LHC, actually expanding our sensitivity for the very short lifetimes of disappearing tracks is going to be quite a challenge. The detector is going to work against us. And so we'll need to work on innovative techniques in order to explore the full range of lifetimes and how that translates to the difference in mass in the supersymmetric case. Okay, to conclude, so there has been enormous work by the community to study potential physics reach at the high luminosity LHC. This, of course, is just the beginning. So as Tulika said, it's a very exciting time to be involved in the LHC program. Not only do we get to work on exciting and important run 2 and run 3 measurements and searches, the community is also involved extensively in the hardware upgrades for the detector. And it's a great time to be involved and actually shape the future measurements and searches that we plan to do. And with these measurements and searches, we plan to have extensive capability to probe both the standard model and beyond. Thank you.
Thank you, Laura. Thank you very much for giving us a glimpse of our exciting future. It was wonderful. We have a few questions, so I take them in the order they came in. So Keith Ellis is asking, it is now decided that both Atlas new small wheels will be installed for 1.3?
That is a good question. I will say it is not yet final.
Okay, thank you. The next question from Richard Ruiz. So he's asking, according to slide 8, I get the impression that official HAPX projection for HL-LHC assume that theory uncertainties reduced by 50%. So is that correct? If so, is there motivation for this assumption?
Yeah, so that is the assumption that's made. The motivation for that assumption is partly looking back over the last 10 or even longer years and seeing, sort of trying to extrapolate the general trend, and also just saying, we expect things to improve. In the theory uncertainty, we expect, for example, generators will improve, and the uncertainties that we have from the generators that are related to that will therefore decrease. And so in some sense, 50% is also just an arbitrary number. But in many cases, I think I highlighted a few of these, we try to show the impact of these assumptions. And so it's not that this is the exact number we expect, but, to try to understand and maybe, let's say, motivate in some scenarios where these uncertainties are very important, and to see how reducing them can have an impact on our precision.
So it gives motivation to the theorists to work even harder.
Yes, we expect, that the theorists along with us will be working in the next 20 years.
Yeah, will keep us busy. And I'm sure in the SNOMED studies that will be more explored in more detail, right? So what it takes to get to that stage. Okay, thank you. The last question, again by Keith Ellis. Do you know why the Higgs 2 invisible in BBF is sensitive to GLU-H normalization? That's a question for slide 20.
I definitely have to go to the slide to see if I can answer this. That is a good question. So this, what I'm showing here is actually, I believe this is a combination from multiple channels. While it's dominated by VBF, it's not the only one that plays a role.
I see. Okay. Yeah, remember to everyone, there is time in during coffee break to go into this in more detail and to chat about more questions. Okay, so thank you very much, Laura. These were all the questions, and thanks again for this wonderful talk. It was really